Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. What did we cover so far? Okay, evaluation. Yes. How to build test collections. This is evaluation, part of the evaluation. Yes. How to weight terms. In the context of what? In vector space models, which was the first time to do a ranked retrieval, right? Yes. What else? TF-IDF was part of, and cosine similarity was part of the ranked retrieval session last time. What was before evaluation? Boolean retrieval. Okay. And what was before Boolean retrieval? Introduction. Right? Okay. Okay. Good. What was before the introduction? Welcome. Okay. Today, inshallah, will be the second ranked retrieval session. Inshallah, very interesting session, at least to me. I hope that, inshallah, it will be interesting also to you. This is called language modeling, and we'll know very soon why we call it that way. So first, let's talk about the general idea of language modeling, which is probabilistic modeling. Okay. Why we care about probability in IR? And you studied multiple, I think, probability courses, right? Beginner and advanced, right? Why should we care about probabilities in IR? What is the relation between IR and probability? What could be the relation? Why should we care? Yes. How?
When I search, I know that it's 100% more chance for this document to be relevant.
Okay, so you're saying that we when we get search results, we are not certain about the relevance of the search results, right? So there is uncertainty that is inherent in IR. And the best way to characterize uncertainty is the probability theory, right? That's the tool that we use always when we have something that is uncertain. To deal with it, we have to use probabilities. Okay, so that's exactly why we care about probabilities in IR. Type. The first time we heard about probabilities and using probabilities in building retrieval models was by Steve Robertson, who coined or who introduced what we call probability ranking principle. Probability ranking principle. What is this principle? Exactly, this is what the principle is. We'll read it together and we'll try to understand what it means. So I will give you 1 minute just to read it, and then we'll go through it together. Done? So what did you understand from that? Yes? Can you raise your voice, please, or move forward? Yes?
When we do the search, and look at the documents, the ranking of this document depends on the most probability for the document to be at the top and easy to.
Does it really say that the highest, the one with the highest probability will be on the top? Yeah. Okay, it's related to what you said, but it doesn't say actually that the first one will be the highest. Actually, it recommends that if you rank the results based on the probability of relevance, in decreasing order of probability of relevance, then this is the best ranking that you can get. Okay, so that's the idea of the principle here. If we rank it, of course there are some conditions, we'll talk about them now, but if you rank it, the search results based on the probability of being relevant to the query, then this is the best ranking that you can get. Now let's go through it in more detail. So it says that if a reference retrieval system, if a reference retrieval system's response to each request is a ranking of the documents in the collection in order of decreasing probability of relevance. So if I ranked the based on given a query, the response, the request, the response to it, if I ranked the documents in order of decreasing probability of relevance to the user who submitted the request, let's skip this the whatever between the brackets now. The overall effectiveness of the system, what does that mean? That's the performance, right? How we measure the performance, how good the search results are to its user will be the best that is obtainable on the basis of those data. Okay, so that's what we said. Now let's look at what is in the square brackets. These are like the conditions, okay, where the probabilities are estimated as accurately as possible on the basis of whatever data have been made available to the system for this purpose. So there are at least two conditions here. First, the probabilities are estimated as accurately as possible. And what is the second? So the system has access to some data around the query. Given that data that is available to the system, if we base the probabilities on that, and the probabilities are estimated as accurately as possible, then the ranking will be the best possible. Okay, so that's the probability ranking principle. Okay, so if we made our estimated probabilities of relevance for documents as accurate as possible, and we ranked the documents based on that, then we will get a very good ranking, or the best ranking possible. Okay, so that's the principle. Of course, it's easy to say, but it's not that easy to implement. Yes? In order of decreasing probability. Yeah, the highest probability will be at the top.
Excuse me, doctor, what is the second?
Sorry?
What is the second condition? What is the second condition that you mentioned?
The second condition is that I use, in estimating the probability, I use whatever data is available to me as a system. Okay? And we'll talk about what kind of data can be available, I think, in the next slide. Okay? Is that clear now, Taiba?
Yes, thank you, doctor. Thank you.
Okay, now, what does that mean? Let's put that in a simpler way. So if we rank documents, we can rank documents by probability of relevance. So P of R given D, that means that this is the probability of D being relevant. Okay? So if I have these probabilities for every document, and I rank these documents so that the highest probability is the first one, and then the second, and then the third, then this is the ranking that the principle is talking about. Right. Now, the principle said also that we need to estimate the probabilities as accurately as possible. That means that we will do some estimation. We have a somehow true probability that we don't know. Okay? And we have to estimate that probability. Okay, so that's what we have here. So we'll have to estimate the probability as accurate as possible from the true probability. Okay, right. Now, what is the data that is available to us? Of course, the query is available, right? What else is other than the query? Of course, the documents also are available. Yes, the query and the documents are available. What else? If I'm doing web search, what else could be available to the system? No, the weights is what the system is doing, okay? But here we are talking about the data that is available from the search, task, okay? Not what the system will do.
Is the
Relevant
search
judgments
history
are available to the system? Okay, it seems like there is a confusion about this notion of relevant judgments. Is the relevant judgments available to the system when we issue a query? What is the need for relevant judgments? Only for evaluation. Only for evaluation. Okay. If relevant judgments are available to the system doesn't need to do anything. Just return whatever in the judgments, right? So relevant judgments are not there at all. The purpose of having relevant judgments or test collections is just for evaluation of the system, not for running the system, of course. Okay. Type. How about the context of the user? Like, what are the previous queries that the user wrote? That might give also some information, right? What about the profile of the user? Might give also some information, right? What about the history of the queries that the user did, not only in this session, I mean not right before that query, but maybe in the previous days or previous weeks? Okay? All of this information is available, right? Also, we talked about the clicks of the user, right? So many information, lots of information actually can be available to a system. So if we based the estimation of the probabilities on all of this information, and the estimation was as accurate as possible, then the probabilities will be very beneficial, because if we estimated these probabilities accurately, ranking the documents based on these probabilities would be the best we can do. So if we do that, of course, that will give us the perfect IR system, but is that doable? Is it always possible to get these probabilities? Of course, this is not easy. Okay, so we need to think first, how can we estimate these probabilities? And this is exactly the idea that we will go around in this session. Okay, how can we estimate the probability of relevance for a document given a query? Okay, that's all about the probabilistic retrieval models. Time. Before doing that, so that's the main question: how to estimate the probability of relevance. But before doing that, let's think about the true probability. What does that mean? Okay, and we said that we want to estimate the true probability, right? The actual probability. What does it mean to have, for a document to have a probability of relevance? We know probabilities, right? We studied probabilities so many times. But when I'm talking about a document now, given a query, what do I mean actually by that this document has a probability of 0.8, for example, to be relevant? We need to understand that first, right? Sorry? Okay, what does that mean? 80% that this document is relevant. We know that the problem here is that we know that the document, in reality, any document can be relevant or not, right? Right? It's not easy to understand that this document is 80% relevant. Okay, but that's what we want to estimate. So what does it mean? If the relevance is binary like that, or even if it's graded, okay, but where is the notion of where can we get the notion of probability here? Any ideas? And if I told you that let's say that one of you attended one of my courses before, right? What is the probability that I cancel classes? How can you estimate it? Okay, so you go through my classes and see how many times my class is cancelled, right? Usually it is near zero. But anyway, let's say that it is not zero. So maybe once or twice I cancel the class, so you divide by the total number of classes, That will be the probability of the class being cancelled. But does that mean, let's say that this probability is 0.2, 20%. Does that mean that every class, the class is cancelled 20% of the time? No, right? It's that over time, okay, 20% of the classes are cancelled. And that gives us the meaning of having a probability of 20% to cancel the class. Right? That's the meaning of probabilities in general. Now, back to relevance. The document is relevant or not, right? It's this way or the other way. What does it mean to have probability 90% to be relevant? Where is the thing that we can count here so that we understand the notion of probability? Now, let me ask you another question. Huh? If I didn't do this probability before, this query before, maybe you cannot get anything. Yes. So I think we mentioned that before, that relevance is subjective, right? If I give you the query in the document, you might say this is relevant. If I give the same pair to another person, he might say that's not relevant. Okay. Now, can we get the notion now of probability from something like that? If I told you now this document is 80% relevant, is the probability that this document is relevant is 80%. Can we interpret it in another way? Exactly. So if I gave this document and the query to n users, 80% of them will say this document is relevant. Okay, that's the meaning of probability here. And that's what we want to estimate. Okay? It might not be, the method that we will use to estimate, by the way, might not be close to what we said, but this is exactly what we mean by relevance probability. Okay? And of course, the search engine doesn't look into your mind to know whether this is relevant or not, right? Although recently there are ways of doing that, by the way. In 2016, the best paper in the best conference in the field, SIGIR, was about something like that. Okay, they had a device that is connected somehow, is trying to track the brain signals when you are doing the search and looking at documents, trying to infer from these signals whether the document that you are looking at is relevant or not. Okay. That's looking into your mind, and that was the best paper. Okay, but of course this is not yet adopted. These are just research ideas. So far, that's not easy. Okay? But as I said, we can understand this probability by what is the percentage of users that can say that this document is relevant. Okay, now if we understand now that we can use probabilities to estimate relevance, then we can see IR as a classification problem. What do we mean by classification problem? You are familiar with classification, right? What is classification problem? Yeah, no, in general, what is classification? I have something that I want to say which class it belongs to. Like if I get a news article and I want to say whether it's sports or health or political or whatever. Okay, so these are classes. If I want to say for a given news article or a book or whatever, which class it belongs to, this is a classification problem. Now I can see IR now as a classification problem. If I can estimate these probabilities, I can estimate the probability that this document is relevant. And of course, 1 minus that probability will be the probability that this document is not relevant. Okay? Now, based on these probabilities, I can say I have two classes, relevant or not. So I will route the document to the, or I classify the document as relevant if the probability of being relevant is higher than the probability of non-relevant, and vice versa, I will classify it as non-relevant. So that's one way of looking at IR. Although this is not actually used. The idea that search is a classification problem is not used, and the simple reason for that is that these two classes are completely imbalanced. And if you think about any query and how many documents in the web, for example, are relevant to that query, and compare the number of documents that are relevant with the number of documents that are non-relevant, it's 99.999999% of the web is not relevant always. Okay, so this is a very extreme classification problem if we think about it that way. So the idea is not to classify every document in the web. The idea is to just find the relevant documents, because there are very few among the entire collection. No, here it's related more to classification, because we have two classes. I mean, clustering, always we don't know the classes. We want to infer something about the structure of the data. Okay, here we know that we have two classes, but the classes are not balanced at all. Okay, so it's better not to look at it as a classification problem. We discussed BM25 last time, right? And we discussed it, or we view it as a variant of what? Of what? Of TF-IDF, right? So we studied the TF-IDF weighting, right? And we towards the end of the lecture, we said that look, BM25 can be seen as a variant of TF-IDF because it has two parts, right? TF part and IDF part. In reality, BM25 was derived based on probability theory, and was actually led by Steve Robertson, whose picture was featured in the beginning. The BM25 model was based on what we call binary independence model. Binary because we only look at the existence of words independent of any other words. That's why it's called also independent. So binary because the term exists or not in the document, and independence because all terms are independent of each other, right? And that's the core idea of bag of words. But it was actually derived using the idea of probabilistic models. Actually, the idea of estimating the probability of relevance versus the probability of non-relevance. We will not go through the details of BM25 today, because we'll actually study another probabilistic model. But I just want to emphasize here that, as I said last time, it is very effective in IR. It was shown experimentally to get very high scores in many tracks. So, and it is actually being used currently in search engines as one very effective feature. It is based on probabilistic model, but we will not study it in detail. What we will study is another probabilistic model called language models. Okay, so that's now will be our focus. Any questions so far? Type. What is the main question that we'll have to answer when we talk about probabilistic models? How to compute the probability, right? How can we estimate the probability of relevance for a given for a document given a query, right? That's the main question that we'll have to answer. Type. Let's say that we answer this. Let's say that there is a way to estimate the probability of D given Q. D as a document, Q as the query. Then what should we do? Yeah, we rank the documents based on these probabilities. The highest probability, the one with the highest probability would be at the top and in decreasing order. Okay. Now, before we get into what we mean by a language model, let's think about what we call noisy channel model of IR, which is the classical model. What is the classical model? The searcher has an information need, and there is a collection that he wants to find documents that are relevant to that information need in. So what does that classical searcher do? He represents this information need into a query, right? And issue that query to the system. Now, the task of the system or the machine is to match the collection or the documents in the collection with the query. Okay, so that's the classical way of looking at the IR problem. Now, why is it called noisy channel here? Yeah, because it's like the query has some noise. Of course, it might not match exactly what we have in the collection. Okay, so that's why it's called noisy channel here. Now, the other model that is based on what we call language model goes that way. In the previous slide, we said that the searcher or the user has an information need in mind, right? Which is the classical way. Here it's different. The user or the searcher doesn't have an information need, but he is thinking about relevant documents. So he has a document in mind. He knows that there is a document in the collection, and I want to retrieve that document. Okay? This is different from what we said in the previous slide. In the previous slide, he has an information need. He is not linked to what is in the collection. He wrote the query and then hopes that the system will match effectively the query with the documents in the collection. Here, the searcher starts with thinking about a relevant document. Okay. Now, if I know that there is a relevant document that I want to get, then of course I will try to write in the query terms that I believe are in this document. Okay, so I will write the query that with words that likely to appear in that document. Okay, now the system will, in order to do this matching, we said that the query will likely to appear in the document, right? So if we think that every document has a model, and that model, we use it to generate queries from, okay, then the best document here that will match this query will be the document that this user has in mind, because it's most probable to generate that query from that model. Let me say it again. We know that now that the user has a document in mind, so he is trying to type as a query words that are most probably will appear in this, or actually appear in this document. Okay? Now, from the other side, from the system side, each document has what we call a language model. Forget about the exact meaning of language model now. Just think that this language model is a way to generate, of course it's a model of a document, but it is used to generate queries from that document. So if that document has, let's say for example, is talking about Qatar University, okay, then you will find that this document has a probability with higher chance to generate a query that is Qatar University, or Qatar, or Doha, or buildings of Qatar University, things like that, right? More than talking about Liverpool and Muhammad Salah, right? Because it's talking about that topic. Okay, so you can think of that language model this way. It captures the topic of the document, And there is a way to know the probability of generating a query from that model. Okay, now since the user has that document in mind, then if we estimated the probability of generating the query from every document in the collection, then the one that has the highest probability of generating that query is relevant, or hopefully relevant, or potentially relevant to that query. Okay, is that clear? Yes. Yes, yes, it's not related to the query, because this model, that's a very good question. These models are built independent of the query. These are models of the documents. So every document has a model, and this model is used to generate queries from that document. Okay, independent from the query. Now, at the time of retrieval, we need to match both. So the model that has very high probability of generating that query is most probably relevant to that query. Okay, so that's the idea. I hope that now it's more clear. Yes. Yes, Ahlam first, yes. Exactly, yes, yes, exactly. Yes, Mariam. We'll talk about how the model, we construct the model later, okay? But let's think about it that way. The model is like a tool that we use to estimate probabilities of generating queries. Okay? Yes. No, I can estimate the probability of generating any query from the model. So I can reuse the model as many times as I can, because every time I tell them, or I ask the model, what is the probability that you can generate, if it's a human, okay? You can generate that query. It will give me a number, okay, and so on. Fine. So here you can say that there is a generation process. We will estimate this probability now. What is the probability of the query Q that is written by the user given the model of the document D? And we do that for every document, theoretically. Okay? And if we do that, then we can rank based on this probability. Of course, we didn't say yet how to estimate these probabilities, but this is the concept. Okay? So the language modeling approach to IR directly exploits that idea, that the user has a document in mind, not an information need. He has a document, so he's trying to generate a query that is most probably represent that document. Or in other words, most probably will be generated from that document if I have a language model for that document. So here's the concept again. You need to come up with good queries. Good queries means the terms will appear in the relevant document that you are thinking about. Okay, so you will think of words that would likely appear in the relevant document and use these words as queries. That's the concept. And the document will be a good match if the document model is likely to generate that query. If the document model, we said that we will have a model for each document. Okay, if that model is likely with high probability to generate this query, then it is potentially relevant to that query. And of course that happens with higher probability if the document has these words. Right? That's logical. Now, what is the language model approach? We will build first the probabilistic language model for each document. That is independent of the queries. Okay, so that can be done offline. Then we will rank documents based on the probability of the model generating the query. And we will always use this notion, by the way, this terminology. So this is probability of Q, that's the query, given MD. What is MD? That's the model of document D. Okay, so we use always M to indicate a model, and the subscript is the document that we are looking at now, and Q is the query. Now, what is a language model, and how can we use it to compute these probabilities? That's the next question. So, what is a language model? In a very simple sentence, a language model is a probability distribution over strings drawn from some vocabulary. Okay, what does that mean? We know what we mean by probability distribution, right? What is a probability distribution? If I told you that this is a probability distribution over classes that I took in my career, what does that mean? Yeah, so yeah, let's say that the classes that I taught, yeah, okay, better than the ones that I studied. Okay, the classes that I taught, that's a probability distribution. That means that probability that I teach IR is 40%. Probability that I teach big data is 25%. The probability that I teach data structures is 15%. Okay, so there is a probability for every possible outcome of that event, which is teaching. And the total of these probabilities is 1. That's why it's called probability distribution. Okay? Is that clear? That's a mathematical notion. So the language model is a probability distribution over strings, over mostly words. Over words. Okay? These words are from some vocabulary. So let's say that we have a collection, and the vocabulary is all the words in that collection, or all the words in English. Let's say that. Let's talk about English. Okay, the vocabulary is all the words in English. Now, what do we mean by probability distribution over these words? Every word. What is the probability of every word? What is the meaning of it? The probability that this word will appear or will be used in English. That can be seen as a language model. So think about that for every word, it will have a probability. Of course, the total probabilities is 1. Okay? So that's what we mean mathematically by a language model. First, why is it called language? Because it works on words, right? It gives us probabilities of words. Okay? Now, what do we do with this? What is the meaning of this first? If I have these probabilities there is a probability for every word in English. What does that capture? In maybe let's say that we are talking about books. Okay, so the language model of a set of books will capture the frequency or how frequent the words are used in these books, right? If I talk about children books, this is different from political books, right? So the language model for children books will be completely different than the language model of political books, right? Right? Why is it? Why are they different? The probabilities will be different also, right? Not just the terms. Some terms might not appear at all in one of these two, and the probabilities also will be different. Right. Now, I hope that now you can tell me what is the meaning if there are some words having very high probabilities, and the rest have very low probabilities in that language model. What does that mean? It means that this language or this model is more about these words than the other words. or the topic of that document, if that's the language model of a document, or the topic of this set of documents, if we're talking about the set of books or something like that, or set of documents generally, is more about these words than those words, than the other words. For example, if we're talking about political books, okay, what are the words that you think will have higher probability? Like what? Law, laws, yes. Okay, law. What else? Democracy. Okay, what else? Politics will be there, right? What else? Countries. Yeah. So you got the idea now, right? So these words will have much higher probabilities than other words. Okay. If we took another example, you see that these words, if I'm talking about sports, of course these words probably will appear once or twice, but they will have very low probability, right? So the language model captures somehow the notion of topics. Okay, what are the words that most probably will appear in such type of documents, if I'm talking about multiple documents, or the topic of that document, if I'm talking about specific document. Okay? We are not talking about importance here. Okay. Yes, the words that appear more in more documents, not more in general. Yes, they are less important. Yes. But it depends on how you calculate the probabilities. Okay, we didn't get into that yet. Okay, but if we are talking about a model like what we see here, okay, we'll talk about how we got these numbers. But if you look at the numbers, tell me what is this document about, given these numbers. And we said that the model, the language model, will be distribution over terms or words, okay? Which means that there is a probability for every word here. Huh? Yeah, it's about the campus of Qatar University, buildings and. Okay. Of course, other words might appear, like education, like green. Okay, but with higher probability, you will see that there are words that are more about this topic than the others. So yes, yeah. Yes, we didn't say how yet. Okay, if that's your question. Yeah, that's a good question. What do you think, based on this idea? For every document, yes. For every document, we will have a language model, okay, and we will use it to estimate the probability of relevance.
Doctor?
Yes, we don't have to do it online, of course, right? It has nothing to do with the query, okay, the language model itself. Yes, Muhammad?
Yeah, so why not the collection? Because it seems weird that we're doing a language per document instead of a language per data set.
Why do we need a language model for the collection?
Well, because that's the whole, at least I could be mistaken, but I thought that's the whole idea, is that for the user to be able to traverse through multiple documents.
Okay, but remember that
the best one.
Remember that here, although I will talk about collection in the second part of the lecture, but remember here what is the user model here? The user has a document in mind and he wants to retrieve that document. Okay, so it's not that he has the collection in mind, he has a document, and we want to estimate the probability of relevance for a document. Okay, so we'll compute that for every document. Is that clear now?
I see. Yeah, thank you very much.
You're welcome. So a topic in a document or a query, by the way, because you can think of a query as a document also, although it's a very short document, can be represented as a language model. So actually any text can be represented as a language model. We can get a language model from text in general. And that language model will represent somehow the topic or topics that are in that text or in that document. And of course, words that tend to occur often when discussing a topic will have high probabilities in the corresponding language. Now the main question again, can we estimate probability of generating text from language models, or how? Because the answer is yes, of course we can, but how? How can we estimate probability of generating text from language models? Why is that question important for us? Yeah, because that's the main concept, right? That we were talking about. We want to have these language models so that we can get the probability of generating text from these language models. And if we have this, then we can estimate the probability of generating the query from these documents. The first type of language model that we will study and we will focus actually on is called a Unigram language model. Okay, so here we will assume that the terms are completely independent. So seeing one term in a document has nothing to do with other documents in the same document, other terms in the same document. Okay, so terms are completely independent. That's why they are called Unigram. So if I have a document like that, and terms here are represented by colors, and I have these words, I got these words from generated this word using the model of the document. Okay, I can think of it that way. The Unigram language model means I will draw these words from the document with replacement, randomly with replacement. Okay, so if that's the case, can I compute the probability of getting these words out of this document? If this is the model now, I will get these words by randomly selecting the words from the document with replacement. So what is the probability of having these words, which is text, right? These words are text. Okay, if I know how to estimate this probability, then I know how to estimate this probability for any sequence of words. Okay, so what do you think? How can we get this probability, given what I just mentioned? Yes. Yes. So tell me what is this probability? So you don't think that we need to compute each one? Yes. Yeah, because each one is a random process, right? It's different random process. So I said that this in Unigram language model, it is like selecting words from the words that appear in the document at random with replacement. So every word that I select has its own probability that is independent from the others. Okay, so the probability of seeing this will be the probability of the first one, as I think you said, times the probability of the second, times the probability of the third, times the probability of the fourth. Okay, each one is independent from the other. Okay, right. Now what is the probability of seeing the red one? Bashir? 4/9. How about the yellow one? 2/9. Then? Oh, it changed now? Okay. But we said with replacement. We said with replacement. Okay? So it will be 4/9, and the yellow 3/9. Okay? So this will be the probability of generating this text from the Unigram language model of that document. Okay? So that's an example of a language model. Unigram, because we assume that observing one term is independent of observing other terms in the same document. Okay? So if for example, I saw the word York, it has nothing to do with seeing the word new. The word university has nothing to do with seeing the word Qatar. Okay? That's the assumption here. You might think that this assumption is bad. Okay, but that's the assumption here. With Unigram language model, this is the assumption, and this is how we estimate the probability of generating text from that. And let me emphasize on this notion of generating text. If I have a language model, if I gave you the language model of English, you can start generating text from that language model, by the way, by this process, by exactly this process. I gave you this language model, right, which is a probability distribution over every English word. Okay, so you will randomly select a number and a word from this. Okay, and of course, you can compute the probability of selecting that word based on the probability distribution, and then select another word, then select randomly a third word, and so on. Okay, so that's a process of generating text from language model based on the probability distribution that is induced by the language model. Is that clear? Yes. Which is true in English, right? Why do you want these words? Why don't you want this? We didn't talk yet about using that for IR, right? We are talking about the language model itself now. Okay, so the language model, that's the probability distribution. I can generate text out of that by this random process, and when I generate that text, I can compute the probability of generating that text. Okay, I hope that this is clear now. Any question on that? Because that's core idea behind what we will study in the entire lecture. If you don't understand now, stop me, ask questions. Oh, yes, okay. So now if you think about our context, yes. So let's say that this is our query, red, yellow, red, blue. And now I want to estimate the probability that this query is generated from that document. Okay, so I use the language model of that document. I can estimate the probability. Now, if I do that for every document, I will rank based on this probability. Okay, that's the basic idea. Any other questions? Yes. Okay. I think the confusion here is that because you want to link, which is good, of course, you want to link what we are doing now with the idea of search, right? But this concept by itself is valid whether we will use it in search or not. Okay? We can estimate, given a language model, we can estimate the probability of generating any sequence of words, which is text, from that language model. Okay? So you understand this. Now you are talking about how we can, how can this be used in our search problem? Yes, what we will do is that we have a query, right? So I want to see what is the probability that this document can generate that query. And that document can generate that query. And that document can generate that query. So this is how I can estimate these probabilities. Okay? And if I do that for all the documents, then I can rank documents based on these probabilities. This is the given query. Now, I didn't select anything. This is what the user selected. Okay, so the user issued that query. In that idea, the user has that document in mind. But now the system is trying to do something like reverse engineering. Okay, which document the user had in mind? Okay, how the system will do that? We'll estimate that probability, and the system will say, okay, because it has the highest probability of generating that query, then probably this is what the user had in mind, which means that this is probably relevant to the user, to the information needed. Is it clear now? Yes. No, we'll not talk about that now. Okay? Not talk about that now. Yes. Okay, still there is a confusion here. A language model can be used to estimate the probability of generating any text from it. Okay, so that's one thing. This is what we did here. Okay, given a document, I want to know how much, or what is the probability that I can see these words from that document. Okay, because the language model, that's why I told you about this English example. If I give you the language model of English, you can think of writing a program that will write English sentences. Because I gave you the probabilities of using the words. Of course, it will be very bad because there is no grammar rules and it's Unigram, so it doesn't depend on previous words, for example. But you can generate out of this you can write code, by the way, to do that. Okay, and you can, by this way, you can estimate the probability of generating anything. Yani, let me give you another example. If I give you the model for sports, okay, language model built from many sports documents, many sports news articles, okay, and I told you what is the probability of generating Donald Trump from that language model. It will be very, very small, right? Because maybe Trump was mentioned once, Donald Reagan maybe mentioned another time, so the word Donald appeared once in maybe 1,000 document, and Trump was appeared also maybe once. So the probability of generating Donald Trump is very small. So do you think that a user that wrote Donald Trump as a query wants to see this document? No, this is exactly the concept. Maybe it's another document or another set of documents. Okay? If you apply that on every document, if you estimated Donald Trump, the probability of generating Donald Trump from every document, then you can have an idea which documents are probably more relevant to the query. Okay? So we are not generating queries. The user writes a query, we take this query, and we estimate, we see which of these millions of documents most probably generate this query from its language model. Is it clear now? I think with the examples that we will see, we will get it, inshallah, much better, yes. If you give me just time, if you are patient, yes, yeah. The model is the model is constructed. The model, which is the probability distribution, I want just to make sure that you understand this. Whenever we say language model, it's a probability distribution. Okay? So this probability distribution is computed offline. We will see how. Okay? We didn't say how yet. Okay? But we'll see how. It's very simple. But we'll see how. But it's done offline. It has nothing to do with the query. And if I give you English, okay, and I told you, give me the language model. You will tell me, no, give me quiz first before I give you the language model of English. Oh, the English, the language model for English, the probabilities of seeing words in English has nothing to do with the queries that the user will write. But we will use it. To estimate if the user wants these documents or not, wants to see these documents or not, based on what is written in the query. يعني be patient with me. Ask me again if it's still not clear. طيب, here is two. I think I should have done this slide earlier, even before answering your questions. Let's say that we have these two language models. I have two documents. Okay, every document has its own language model, which means has its own probability distribution, like what we see here. Okay, now I have text, Qatar University Research Grant Profile. Can I compute the probability of generating this text out of these language models or not? I can, right? So what is the probability of generating this text from language model 1? Yeah, multiplication of these corresponding probabilities, right? So it will be 0.2 times 0.01 times 0.0001 and so on, right? So that's the probability. Okay. We'll get to that later. Okay, but let's assume that everything has a probability. So I will get a probability like that, right? Okay. How about the second document? We can do the same, right? So we can do the same and estimate that probability. Now, document 2 has a higher probability of generating this text. Okay? So if that text was the query, and I only have these two documents in the collection, then how can I rank them? 2 is more relevant than 1. That's the application. Okay, that's the application. So now I can say probability of generating that text given the model of document 2 is higher than the probability of generating that text from the model of document 1. So I will rank document 2 higher than document 1 if this is the query. Okay. Yes, but did I say different from that? I didn't say anything about how we get these probabilities yet. What I said that we have these probabilities. Okay, but you saw something like that from the previous slide when we had these small boards, right? But still, I didn't say it explicitly, and it's not far from what you are thinking, by the way. Okay, so we talk. Yes, Taiba.
There's one thing in my mind, like the vocabulary for both document 1 and document 2, they have the same underlying vocabulary. It's just that the probability distribution is different.
Yes, generally it is over the entire probability of English. If you are talking about English here, some of the probabilities might be 0 or close to 0. By the way, that's fine. But generally, it's like when we said in the vector space model, each document is a vector over the entire vocabulary space, not just the words that appeared in the document. Okay? It is over everything. But of course, the probabilities might be different.
Thank you so much. Thank you.
Now, this question, I think I answered it already. Okay? Is that useful? Of course, it would be useful in ranking, right? Okay. Now, yes, Muhammad. By the way, I will finish this set of slides today. Okay? I'm with you until Fajr time. I have to leave by Fajr time.
It's just like
ask all of your questions.
Yeah, it's just like something that immediately comes to mind is that how we're guaranteed the usefulness, because like as we already covered over in binary, ranked search and others, we have stuff like the closeness of the words to make it relevant.
Yes. Where's the question, Muhammad?
So like how is it useful? Because it could be the case that like words exist, but not necessarily like
the question here
the
was
context for the user.
the question here was about how these estimated probabilities are useful in our context, and I think I answered that by saying that although the concept here is general, yani I can estimate probability of generating any text from any language model, but for our context we will use that when we have a query. The text will be the query, and these documents will be the documents in the collection. And based on these probabilities, we'll rank the documents based on these probabilities, and this is how it will be useful in our context. Did I answer your question?
Yes, thank you.
Okay. Okay, so we talked about Unigram language model, right? That's the simplest way of thinking about a language model, but there are more complex. Okay, so the next one is called bigram language model. So in bigram language model, we have a conditional probability distribution. We have the probability of seeing one word given the previous word. Okay? In Unigram language model, we just have the probability of observing a word, independent or not conditioned on what we saw already in the text. Okay? So in bigram, it's conditioned. Now, if I have a bigram language model, and I want to estimate the probability of generating this text out of that language model. In the Unigram, we said that this will be probability of red times probability of yellow times probability of red times probability of yellow, of blue. Now, if that's the sequence, and I assume that I have bigram language model, what will be the probability? What is the probability of observing the first red? It's just the probability of red, right? Type. Then we saw yellow. So that should be conditioned on seeing red. So that should be probability of yellow given red. Then times, you know the chain rule, right? Then times the probability of red given yellow and red. لا والله two givens دي انا ما شفتهاش قبل كده. That's يعني اختراع. You mean probability of red given yellow and red, right? This is what you said, and this is what you meant, I think. طيب, is that right?
It's not, it's given the conditional probability, the previous.
It's written that way. This is the way that I know from what I studied in probabilities before. Okay? When you say probability of x given y and z, this is what you mean, right? Yes, it's and. Okay. Right. Is that correct? We said bigram, and bigram means every word depends on all the previous. I didn't say all the previous, just the previous one, the immediately previous one. That's why it's called bigram. Bi, what do you mean by the way? Bi means two, this word and the previous one. Unigram means one, this word only. Okay? So it's the probability of red given the model, of course. Sometimes we remove the model because it's implicit everywhere. Okay? That's what we did in the Unigram language model. It should be given the model, of course, but sometimes we just remove this given model. This is the probability of red. So this is the Unigram probability because it doesn't depend on anything, and we didn't see anything yet. So that's the Unigram probability. But then we multiplied by the probability of seeing yellow given red times probability of red given yellow times probability of yellow of blue given red. Okay. Now, of course, if we have the language model, we should know these probabilities, and we just multiply these probabilities. So that's different from Unigram, of course. The number, the computation that we will do here will give us different numbers. Okay. So that's what we call bigram language model. Generally, there is what we call stochastic language model. In stochastic language model, we don't only condition on the previous word, we condition on all of what we saw before. Of course, there are many models in between, right? There is trigram and 4-gram and 5-gram. So that's the extreme. Okay. So if I want to compute the probability here of seeing this sequence of words, what will be the probability? First one is the same, right? Because we didn't see anything. Then times yellow given red times red given yellow and red, and then blue given all of the previous three. Okay. Type. If we look at the bigram model back, we need to know these probabilities, right? So these are called the parameters of the model. We need to estimate these parameters. We need to know what is the probability of every word given every other word, so that I can compute the probability for any text, right? And also I need to know the probability of the Unigram probabilities, because it's probable that any word can appear in the beginning, right? So I have to know the Unigram probabilities and the bigram probabilities. Okay, so these are the parameters of the model that we need to estimate. How about Unigram language model? Just the no, not the same. Not the same. Let's go back to the Unigram language model. This is the Unigram language model, right? What do we need to estimate? What are the parameters here? One parameter per word, right? But for bigram, how many parameters per word? Not two. Not one. V, that's the number of terms in the language model. Because I need to know, let's say that we have here bigrams. Yeah, I need to know probability of red given blue, and given yellow, and given red, and given any other color. Okay, in general. Okay, so I need to know that in the language model, so that I can compute the probability for any text. Okay, so that's why I said that this is more complex, because there are so many parameters here. Actually, it's square of the number of parameters that we need in the Unigram model. Okay, so here we have, if we have n terms, so for red we need n parameters, for yellow we need also n parameters, and so on. So we have n square number of parameters. But for Unigram it's just n, because we have just one probability that we need to estimate for every word. So Unigram, of course, is much simpler. But as you see, which one is more powerful? Bigram, of course. And even the stochastic one, of course, is the most powerful, but it has so many parameters, because you have to estimate for every one, given just one word, given 2 words, given 3 words, given 4 words. Of course, that's too much. Okay, so just an overview before we stop. Unigram and higher order models. This is how we compute the probability in Unigrams, Unigram language model. This is how we compute it for bigrams, and this is how we compute it for the stochastic language model. Of course, the first one is much simpler, easy, and also effective in IR. Yani you might think that this is very simple. It's completely independent model, right? I mean, the terms, there is an independence assumption here. Every term is independent of the other. Okay, so seeing Qatar and before university, I mean, seeing Qatar doesn't tell what is the probability of seeing the next word at all. Okay, of course, the word university has higher probability maybe than others in our context, but the Unigram doesn't capture that. Unigram just capture the independent probabilities. but despite that, it is very effective in IR.